Hello everybody, this is Daniel Crane, and I'm going to be talking about an eigenvalue, eigenvector example problem. Specifically, I'm going to be talking about that last problem on the practice exam that I posted on Canvas. So feel free to use this video in addition to the answer key that I'll post later so that you can further your understanding of this sort of problem. Okay, so here's the problem. Find the eigenvalues and eigenvectors of the below matrix. Use your solution to diagonalize the matrix A if possible. So we have the matrix given right here. Alright, so let's review the definition of an eigenvector. We say that if x is a non-zero vector, then it is an eigenvector of A with the corresponding eigenvalue lambda if AX equals lambda x. Now this is equivalent to AX equals lambda IX, where I denotes the identity matrix, okay? Because I times any vector is just that same vector. Alright then, so what I'm going to do is I'm going to subtract the lambda IX to the other side and factor out the vector x. So I have the equation A minus lambda times IX equals 0. So, the eigenvector x will exist if we can find a non-zero solution to this homogeneous equation. Alright, so here's the question. When does A minus lambda IX equals 0 have a non-trivial solution? When can I find a non-zero vector x such that this holds? Well, let's just point something out first of all. If A minus lambda I is an invertible matrix, well then I can just take the inverse of both sides of this equation. And then when I do that, I end up getting x equal A minus lambda I inverse times the 0 vector. And any matrix times the 0 vector is equal to the 0 vector. This would show that x is equal to 0. But that's the trivial solution. And we want x to not be equal to 0. Okay, so if A minus lambda I is invertible, then there's no solution to this. We can't find an eigenvector. So what do we do? Well, instead, we want to know when A minus lambda I fails to have an inverse. Now, by the invertible matrix theorem, this will occur when the determinant of A minus lambda I is equal to 0. So we're going to investigate that. So we wish to compute the determinant of the matrix A minus lambda times the identity matrix. And if we do the matrix addition, or subtraction, I suppose, then we just get the minus lambda expressions all along the diagonal. Alright, so we are going to take the determinant of this matrix, and we're going to try to show when it is we're going to try to determine when it is equal to 0. Alright, so I'm going to use a cofactor expansion to compute the determinant. And I'm going to go to pick the first row here. So I've taken 1 minus lambda times the determinant of the submatrix that I obtain when I eliminate the row and the column that 1 minus lambda is contained in. So I have to take the determinant of this 2 by 2 submatrix. And then I subtract negative 1, so therefore I add 1, times the determinant of the submatrix that I obtain when I eliminate the row and the column that negative 1 is contained in. And so I obtain this submatrix. And then I take 0 times the determinant of the submatrix that I get when I eliminate the row and the column of 0. And I get this. Now this, of course, doesn't really matter that much because I'm multiplying it all by 0, so that's third term goes away anyway. Having computed the determinants of that first matrix, I get 2 minus lambda times 1 minus lambda minus negative 1 times negative 1. And then I get 1 times the determinant, which is negative 1 times 1 minus lambda minus 0. Okay, so at this point, this is a point where many students, I think, will make mistakes. You might be tempted to try to just start multiplying all of these terms out and then trying to simplify them later. But we can actually take advantage of a few nice properties that this expression has. Specifically, notice, I have a 1 minus lambda here, and that's being multiplied by this entire expression, but I also have a 1 minus lambda here. So I can actually factor a 1 minus lambda out of that entire expression. And this is what I obtain when I do that. I have 1 minus lambda times 2 minus lambda times 1 minus lambda minus 1, and then I have this minus 1 from this expression here. So now I can just leave this 1 minus lambda alone, and then I can just work and start multiplying out everything in the square brackets, and that's only going to be a quadratic, so things will simplify a little bit for me. So when I multiply all of this out, I get 1 minus lambda times the quantity 2 minus 3 lambda plus lambda squared minus 2. Now notice I have a 2 and a minus 2, and those will cancel. This gives me 1 minus lambda times lambda squared minus 3 lambda. But then notice I have a factor of lambda in each term, so I can factor a lambda out. And this gives me the expression right here, 1 minus lambda times lambda minus 3. This expression is called the characteristic polynomial for the matrix A. And this characteristic polynomial will basically allow me to very easily see what my eigenvalues are. Remember, the question we were asking is, when is the determinant of A minus lambda I equal to 0? Well, that's the same as asking, when is this polynomial equal to 0? And I think it's pretty easy to see when that is true. The determinant of this matrix will be equal to 0 at 3 points. When lambda is equal to 1, when lambda is equal to 0, and when lambda is equal to 3. So this means that the eigenvalues of the matrix A are 0, 1, and 3. Now we need to find the eigenvectors associated with each eigenvalue. And we have to do the same sort of process 3 different times, one for each eigenvalue. So let's start by finding the eigenvector associated with lambda equals 0. We do this by finding a non-trivial solution to A minus 0I x equals 0. Notice, all I've done is taken lambda and replaced it with 0, and I'm trying to find a non-trivial solution to this equation. So, what I'm going to do is I'm going to take my matrix A, and everywhere I see a lambda, I'm going to replace it with 0. That gives me this matrix. So I'm going to try to solve the augmented matrix. What you have here is this is the matrix that I get from replacing lambda equal to 0, and then I have these, I augment this column of zeros, and I'm trying to find a non-trivial solution to this equation. So what I'm going to do now is I'm just going to row reduce, okay? And I'm going to breeze through this a little bit quickly, so feel free to pause the video if you need to slow it down at all. Alright, this is in reduced row echelon form. So if we look at that first row, I have the equation x1 minus x3 equals 0, and the second row gives me x2 minus x3 equals 0. Alright, so x3 is a free variable. I can pick whenever x3 variable I want, and so it's usually convenient to just choose x3 being equal to 1. So if x3 is 1, then x2 and x1 are both equal to 1. So this means that the eigenvector associated with lambda equals 0 is 1, 1, 1. The vector 1, 1, 1 will solve the equation A minus 0I x equals 0, and you can check that. So now we just need to perform the exact same procedure for lambda equals 1 and lambda equals 3. So for lambda equals 1, I'm going to replace lambda with 1 and try to find solutions to the homogeneous matrix equation A minus 1I x equals 0. This involves setting up an augmented matrix, okay? What I'm going to do is I'm going to take that matrix with the 1 minus lambdas, and everywhere I see a lambda, I'm going to replace it with 1, and I'm going to augment a column of zeros. So again, we just need to row reduce. So I'm just going to go through that, and feel free to pause if you want to slow things down. Alright, I've row reduced it as far down as I can possibly get it, and the first row tells me that x1 plus x3 equals 0. And the second row tells me that x2 has to be 0. So again, x3 is a free variable. So for convenience, let's just choose x3 to be 1. And then that would mean that x1 would have to be negative 1 and x2 would have to be 0. So an eigenvector associated with lambda equals 1 will just be negative 1, 0, 1. Alright, so I'm just going to leave this entire slide up for you guys. It's the exact same procedure, but with lambda equals 3. Just replace lambda with 3 and try to solve the system A minus 3I x equals 0. This produces this augmented matrix shown here. And then I've got a row reduce. And that first row tells me x1 minus x3 is equal to 0. And the second row tells me that x2 plus 2x3 equals 0. So again, just for convenience, let x3 be equal to 1, and then that would mean that x1 is equal to 1 and x2 is equal to negative 2. So an eigenvector associated with lambda equals 3 is 1, negative 2, 1. Alright, we're almost done. So altogether, the eigenvalues, eigenvectors of this matrix are given by, and I just list all 3 of the pairs right here. So now we can diagonalize the matrix A by using the above information. We want to write A equals P, D, P inverse, where P is an invertible matrix of eigenvectors and D is a diagonal matrix consisting of eigenvalues. And the way we do this is we take the matrix P And P just consists of all of the eigenvectors. Okay, we take this vector, and this vector, and we concatenate them all together into a 3 by 3 matrix. And then D is just the diagonal matrix consisting of the eigenvalues, with 0, 1, and 3, and then 0 everywhere else. Now, one thing to note, because I explicitly put this eigenvector first, that means that I need to put its associated eigenvalue first. So if I put a 3 here and a 0 here, that would not be correct. I need to make sure that my eigenvalues and my eigenvectors are in the same order. That means that I can diagonalize A. I can say that A is equal to the matrix P times the matrix D times the matrix P inverse. Now, in an actual exam problem, I don't really care if you don't actually explicitly find the inverse of P. You can just leave it as I've left it here. However, if you do have some extra time, you can work out what the inverse of P is on a piece of scratch paper perhaps, and then if you multiply all these three matrices together, you should get exactly A. Alright, that concludes this video. Thank you for watching.